Hi, this is Dr. John Bergduff. In this video, we're going to solve rational inequalities. Now, there are many methods that different professors and different textbooks show for solving rational inequalities. Rational inequalities are simply inequalities that involve some sort of fractions in which there are variables in the denominator, perhaps in the numerator too, but definitely in the denominator. Most of the methods that are shown involve something called test points and maybe sign charts. And I don't want to get into any of those there in this video, but you will find plenty of videos that, even on my own channel, that describe how you can solve rational inequalities using sign charts and test points. What we're going to do in this video is show that if you know already how to graph rational functions, graphing rational inequalities is as simple as looking at the graph of the appropriate function. So let me show you how that works. So suppose you have a rational inequality like this one. And there are three steps that you're going to follow. First thing you're going to do, and this would be, by the way, what you would also do for pretty much any method for solving rational inequalities. The first thing you do is you rewrite the inequality with 0 on the right side, particularly the right side is best, and one simplified fraction on the left side. So what does that mean? Well, for one thing, we are going to, hold on. Problem with the pens there. We are first of all going to subtract 2 over x minus 1 from both sides. So we would get 3 over x plus 1 minus 2 over x minus 1 is greater than or equal to 0. Then we are going to find a common denominator, and that is fairly simple. If I take the first fraction and multiply numerator and denominator by x minus 1, like this, and take the second fraction and multiply numerator and denominator by x plus 1, there will be a common denominator of x minus 1 times x plus 1. And that'll all be greater than or equal to 0. Multiplying out the parentheses, we would get 3 times x minus 3, and then multiplying the negative 2 across the second parentheses, negative 2x minus 2. The denominator would be the product of x plus 1 times x minus 1. All that would be greater than or equal to 0. Combining like terms, we would have in the numerator x minus 5, and the denominator would remain x plus 1 times x minus 1. Greater than or equal to 0. And that's exactly what we're looking for there, one simplified fraction on the left side. If you prefer, and there was going to be a reason why this will be useful, you can multiply out the denominator using the FOIL rule, and it will turn out to be x squared minus 1. But it's good to remember that that x squared minus 1 factors like this for the work we're going to do. So that's the first step. Now, what's the second step? Well, let's take the function as we have rewritten it, and here it is in simplified form, just like we had rewritten it. Let f of x be the left side of the inequality, and sketch the graph of f. So we are now going to look at how do you graph the function f of x equals x minus 5 over x squared minus 1. Now, I have a couple other videos on my channel that talk about how to graph rational functions. I am going to recommend that you take a look at those if you've never seen graphing rational functions before. I'm going to do this kind of fast. So when we graph rational functions, the best thing to do is to look for, first of all, the y-intercept. The y-intercept is found by letting x equal 0, or in other words, finding f of 0. F of 0, if you plug in 0 for x, you will get -5 over -1, and that tells me that the y-intercept is at 5. So that's at least something. We also find the x-intercepts, and that is found by setting the numerator equal to 0. So x minus 5 equals 0, and that would give me x equal 5. So amusingly enough, the x-intercept and the y-intercept are both at 5. So the x-intercept and the y-intercept, that's one thing you can do. Now, next, we are going to look for the vertical asymptotes and the vertical asymptotes of a graph occur where the denominator is equal to 0. In this case, it is actually slightly nicer to remember that the denominator factors as x plus 1 times x minus 1, and setting each factor equal to 0, we get -1 and +1 as the locations of our vertical asymptotes. So I'll draw those in. There's +1 and there's -1 as vertical asymptotes. So that's very helpful. And finally, we want to look at the horizontal asymptotes. So let me talk about that. So the horizontal asymptotes, you might remember, depend on the degree of the numerator and the degree of the denominator. In our case, the degree of the numerator is less than the degree of the denominator. And when that happens, that means that the horizontal asymptote is going to occur at the x-axis. So I'll draw that in. Notice that there's a point on the graph that is also on the horizontal asymptote. Remember that a graph can cross a horizontal asymptote, but as you go farther and farther to the right and to the left, it will approach that asymptote. Now, this is actually enough facts that we could draw the graph. In my other video, you'll see that I talk about starting with the y-intercept if you have one. I know that the graph has to go through the point 0,5, and it has to approach the vertical asymptotes. And you might wonder, well, does that mean possibly that the graph would go like down, like that? But it can't do that, because if it did, it would cross the x-axis somewhere and have an x-intercept someplace between -1 and 0. So that, in fact, can't happen. We're going to erase that and fix my vertical asymptote. I can't, in other words, have the graph approach -infinity as it approaches actually either of those vertical asymptotes. So the only way that can happen is for the graph to come sort of down the vertical asymptote on the left, turn around and go back up, and make a shape kind of like that. Now, I don't have a single point plotted to the left of the vertical asymptote at -1. That is actually okay because the multiplicity of the vertical asymptote at x equal -1 is odd. We know that the branches of the function, as they approach that vertical asymptote, will be going in opposite directions. So if the branch I've already drawn is approaching positive infinity, then the branch to the left side of that vertical asymptote must be approaching negative infinity, turning and approaching the horizontal asymptote. So that branch will have to look something like this. And correspondingly, on the other side of the rightmost vertical asymptote, that graph also must be approaching that vertical asymptote as going towards negative infinity. Now it's going to cross the x-axis at 5, but because that's a horizontal asymptote, it's going to have to kind of hug that asymptote on the upper side and kind of continue to approach it. And again, if you're not familiar with graphing rational functions, that might seem like a bit much from just plotting a couple points, but that takes care of it. And again, you're welcome to watch the videos that I have on graphing rational functions. I think they'll be helpful. All right, so now we've got this graph. What are we going to do with that? Well, here's the graph recreated. As I look at the inequality as I have rewritten it, and as I've redefined it as f of x greater than or equal to 0, as I look at the graph, I'm going to just think about what intervals on the x-axis are consistent with whether you want the graph to be above, below, or on the x-axis. Now here what I'm talking about is that I'm asking where is f of x greater than or equal to 0? F of x is greater than or equal to 0 for any values of x that are above the x-axis. So my solution is simply to look at this graph and say, well, where's the graph above the x-axis? Over what intervals on the x-axis is the graph above the x-axis? And you can see that the graph is above the x-axis in this little sort of U shape up here. So that would correspond to the interval from -1 to 1, not including either endpoint because there are vertical asymptotes there that are not part of the graph. And although this could be easy to miss, the graph sneaks above the x-axis over here as well from 5 to infinity. And because this says greater than or equal to, we actually want to include the 5 because the graph is on the x-axis there. So 5 with a bracket to infinity. There's 2 intervals involved, so you say union. No test points, no sign charts, but you have to know how to graph the rational function. So an interesting approach that can be very useful if you aren't greatly worried about how you got the function. You could graph it using a graphing calculator or using a graphing tool online like Desmos and simply look at the graph. So I hope that is interesting as an alternative approach, and I hope it'll be useful to you.